Right? Today, last chapter in Calc 3, vector analysis. Starting out with vector field, a function that assigns a vector to a point in the plane or in space is called a vector field. Lots of examples of vector fields. Air flowing over a car, aerodynamics, the vector field. Electronic vector field, Newton's law of gravitation. These are all vector fields. A vector field in a plane, over a plane, okay, assigns a vector for every point in the region. A vector field over a solid region is a function that assigns a vector to every point in the region. Gradient is an example of a vector field. So lots of examples of vector fields. A lot of examples of vector fields. And so with vector fields, you'll see that 3-dimension here, right? Gravitational field, everything, all the vectors are being pulled in this way. The closer you are to this point of origin here, the bigger the vector. So go look at some of the examples of vector fields. I think you'll see it pretty easy. We'll sketch some of them. Again, you can't schedule every vector, but go look at those 3 examples in the book and see what we can get there. Now, what we do want to talk about with vectors and vector fields is whether a vector field is conservative or not. Conservative. So a vector field, okay, is called conservative when there exists some function you can take the derivative of such that the gradient of that function is the same as the vector field. That is called the potential function. That is called the potential function. For example, 2xi plus yj, vector field. Every time you put a value in, you get a vector. Right? So all those vectors, this vector field is conservative because it should be pretty obvious to see that to get 2x, the derivative of what is 2x? Well, that's x squared. And the derivative of what is y? Well, that's 1/2 y squared. This function, if you take the gradient of that function, you get this. So this function is called the potential function. So we want to develop a couple of tests so that we can determine whether a function is conservative or not. So if you have a 2-dimensional function, I and j, I component, that's x, y component, that's j. So this vector field is conservative if and only if you take the j component related to y and take the partial derivative in relationship to x, and you take the I component related to x, take the derivative of that in relationship to y. If those 2 results are the same, then it is a conservative vector field. It is a conservative vector field. So if you look at, here's m and here's n. So we take the derivative of this in relationship to x, you get y. Because derivative of x is 1. Take the derivative of this in relationship to y, you get x squared. They're not the same. This is not a conservative vector field. It is not a conservative vector field. Here's another one, 2xi, yj. You take the j component, take the derivative relationship to x, you get 0. You take the m component, the I piece, in relationship to y, you get 0. That's the same. Therefore, this is a conservative vector field. This is a conservative vector field. That's 2 dimensions. 2 dimensions is pretty simple. With 3 dimensions, we have to first figure out this thing called a curl. A curl is a cross product. So we're going to take the cross product. That's I, J, K. It's the cross product of the derivatives, partial derivative of x, y, and z, of the function MI, NJ, PK. And if you do this determinant, you will get this result. If you do this determinant, you will get this result. We've done a few of these kinds anyway to practice them a little bit more. So here's the result. Okay. If, when you take the curl of the three-dimensional vector field and you get the zero vector, 0i, 0j, 0k, then the three-dimensional vector field is conservative. The three-dimensional vector field is conservative. So those are the two ways of determining if you have a conservative vector field. If you have a conservative vector field. Now, I'll tell you about one other piece that we come back and use later. But if you have a vector field, you also have something called the divergence. And the divergence is the dot product with the derivatives. The curl is the cross product with the vector field. And so this guy is called the divergence, and we'll talk about the divergence later on in the chapter.